Now we're getting into one of the most interesting things about complex numbers, which is putting them on a graph. And prior to this, I think the best rule about graphing imaginary things has been don't. Right? Typically, we only graph the real part of numbers, and that's when you have your polynomial graphs and your rational graphs and trigonometric graphs and so on. But now we really are going to graph the imaginary parts, and we need to change our coordinate system to do that. You'll notice I now have a real axis and an imaginary axis. The real axis is for the real parts, the imaginary axis is for the imaginary parts. And it's pretty self-explanatory. Let's take this first one. W equals 2 plus 4i. Well, the real part is 2. So that's going to be somewhere over here. And the imaginary part is 4. So that's going to be somewhere over here. You see where those intersect? It's going to be right there. So there's W. And now, if I do the next one, which is going to be in blue, z equals 1 minus 3i. Well, that's going to be x equals 1. And then we're going down 3 over to here. So there's where our point lands for z. And eta, this last one here, first we just need to do a little math here. What's w plus z? Well, this won't take long. 2 plus 1 is 3. 4 minus 3 is 1, so we have 3 plus I. So if we try to put this on our graph, you'll see eta is over 3, up 1 to this spot right there. Okay? So now we have our 3 dots on this graph. And what gets interesting, you'll notice there's a little bit more before we're done with this problem, if you're working through the homework. It says mark 3 points. We did that. Now draw some connecting lines between the origin and each of the points W and Z. Well, don't lose track of which one's which. That's W, the red one. This is Z, the blue one. And now draw 2 lines connecting each of those points to eta, that new one we found, okay? So that goes like this and this. And that's it. Now you're done once you've finished using the graphing tool. What I think is interesting about adding complex numbers together is you always end up with a parallelogram. And basically the reason we're ending up with a parallelogram is because when you're adding complex numbers, that is a commutative process. It doesn't matter if we said w plus z or z plus w, we get to the same place. So in other words, you could go this way to get to that point, or you could go this way, but they are symmetric processes. So that's why we end up with the parallelogram here.